Welcome to another lecture of the AI series. And today we are going to talk about the logistic function and the softmax function. So both of these functions are used when we are trying to categorize something with regression. So first let's see like a small example on why we want to use the logistics function, right? So let's say we have two categories. So this is about the logistic function. Right. And we have two categories. Say let's say cats and dogs, and we have some kind of a machine learning algorithm which gives us a score. It looks at the picture and then lets us know, okay, this looks like a cat this much. So let's say it has a cat score. So it says it looks at picture 1, which is of a cat, and says, okay, this is given 500 cat points. And then we have another picture, this time of a dog. There are like similarities between cats and dogs. So this is okay, 250 cat points. So when we get a number like this, it's not very straightforward to categorize these things. So we would ideally like to know a probability of this picture being a cat and the probability of the second picture being a cat. So we would like to know a probability. So let's say we'd like to, for example, want to know this is like, okay, 75% a cat. We can say almost for sure that this is a cat, and this is like not so much likely that it's a cat. So what we're looking to do here is we want to convert some kind of a score into a probability. So when we want to do this, what we have is that for the score we have S, which is from -infinity to +infinity, and probability, of course, is like between 0 and 1, right? So P is between 0 and 1, and there's a special case with probability that P excuse me, P1 plus P2 should be 1, because ideally we are calculating two probabilities. When we are looking at this, we want to know the probability of this being a cat and the probability of this image being a dog. So there should be the complement of each other. So these are the properties we are looking for. So we are going to convert a score into a probability, and that score is between -infinity to +infinity, and we are converting it into a probability between 0 and 1. Right? So let's see how this is like how this can be done in practice. So let's say we have the probability of let's say up here is cat and down here is dog, and then let's say although theoretically we say it's between -infinity to +infinity, when we are actually giving a value, we know that this is going to be between two specific values in like most of the applications. So let's say for the purpose of this application, we are giving values between minus 500 and 500, right? So we can have something like this, where if it's minus 500, it's definitely a dog, and if it's plus 500, that's definitely a cat. And in between, at the halfway point, this is where we are not really sure, so 0.5. So here, like, we have a couple of problems with this thing. So imagine like we train our model on this data, and suddenly for some reason we get a 600, or here we have a negative 750, something like that. So what happens in the case, these are questions, or like rather problems. So what happens when our S is greater than 500, or our S is less than negative 500? This is the first problem. The second problem is, imagine we had an image up here which scored 500. So now it's scored a little, like, we made a slight change to the photo, and now it's like let's say 490. There's like 10 points different. So look at this difference here, and imagine we have a picture which is like really ambiguous, and it gives us a 0, and we made some pre-processing to this image which bumped up its score up to 10. So here we can say that we can see that in both cases the change here was the same, but ideally what we would like to see is that when we are like not really sure, like when we are here in the midpoint, if by some pre-processing we gain 10 points, that we'd like to see that expressed a little bit more, like we would like to see that change to be a bit higher, and like similar on this side as well. And actually, like at this like very corner, like we don't really see a big difference. Like there's no real big difference to our probability value when the score changes at the edge cases. So we would like to have something like that, and luckily we do have it, which is the logistic function, which is written as the logistic function. We can call it P of S is equal to 1 over 1 plus e to the power of minus s. So let's see how this works for like the edge cases. When s goes to infinity, what happens? E to the power of so minus s goes to infinity, e to the power of infinity goes to 0. So when s goes to infinity, minus s goes to minus infinity, e to the power of minus infinity is 0. So we have 1 over 1, which is p to the power of s is equal to 1. When s goes to minus infinity, this works the other way around. There's 1 under infinity, which makes p of s go to 0. And when s is equal to 0, p of s is 1 over 1 plus 1, which is 0.5. So we can see that with the logistic function we have something like this. where it is 1 here. As this goes to infinity, this approaches 1. Same here, when it goes to minus infinity, it approaches 0, and in the middle we have 0.5, right? And we can also see how this works with derivatives, because we know that when we want to check when we want to do a gradient descent, we want to get the derivative of it. So let's check the derivative as well. So we have the derivative of the logistic function. So here we have dp over ds, which would be e to the power of minus s divided by 1 plus e to the power of minus s squared. So I'll let you do the derivation, and so here we can divide it into two parts, 1 plus e to the power of minus s times e to the power of minus s under 1 plus e to the power of minus s. So you can clearly see that this is p itself. So with some calculations, you can see that this would be 1 minus p. So this is important, because let's see when this derivative is at its highest. So we know that when something is like this, p times 1 minus p, this whole thing is largest when this is actually like half. So half times half is the biggest this number can get. So we can see that in the middle of this graph, that's where the derivative is the highest. And at the edge of the graph, where, for example, when p is either 0 or p is 1, this derivative goes to 0, right? So when p is 0, you know that 0 times 1 minus 0 goes to 0. When p is 1, 1 times 1 minus 1, this also goes to 0. So as you can see, the derivative also makes sense. So this is the logistic function which works for a binary categorization. So when we want to classify something into two classes, we can use the logistic function, and this is differentiable, so it works with the gradient descent as well. Alright, so now let's see the slightly similar softmax function. So this okay, let's see this softmax function. So this is a generalization of the logistic function. So usually it's known with this symbol. So well, let's maybe just use p, so that's easier. So again, we'll use sp of si is equal to e of si divided by, so let's see, j to k e of sj. So this is the softmax function, but I'll explain how we get there as well. So similar to last time, so let's say that we have a whole list of animals, and we give them like different scores. So we have a cat score, a dog score, a cow score, a donkey score, etc. And we have this list of scores which will be again between minus infinity and infinity, right? And then depending on these scores, we can give a probability for each class. So class 1 probability, so we'll say like P1, P2, P3, etc., because we have S1, S2, S3, etc. as the scores. Similarly, what we want to do is to convert our score into a probability. And again, our goal is to get a probability so that Pi is in the range of 0 to 1, and that sum of all Pi would be equal to 1. So having this goal in mind, one thing we can do is, you might already be thinking of this, Si divided by the sum of Sj, so sum of all scores. So this works all right, but let's take a scenario where we have the scores 0, 1, and 2. So here we get the probabilities 0 divided by 3, which is 0, and I'll just like 0, and then 1 divided by 3, then 2 out of 3. So this looks nice. But what if we get something like 100, 101, and 102? So this gives us like probabilities, I would say, around this, like this would be around 0.33, 0.33, and I'll take this one to be 0.34 to make a full one. So this is not that great for us to classify, right? So we want something that shows us the difference as well, so which makes us choose a category much easily. So here is where we use the sort of the logistic function. So we say probability of I is equal to e to the power of Si divided by the sum of all the scores to the power of e to the power of s and sum of all that. So when we take it like this, you can see if we add a fixed number to this does not make a difference, because by the rule of powers, we can consider this to be, we can separate that C out, and we can see that it cancels out. So in this case, both 0, 1, and 2, and 100, 101, and 102 would give us the same probability distribution. So this is why we like the softmax function, and this is a generalization of the logistic function into a basically k dimension. So we can say that the softmax function is a generalization of the logistic function. And if we are using this simple sigma for the softmax function, we can say that it converts something, it converts an k-dimensional vector of real values into a k-dimensional vector between 0 and 1. So this is basically the logistic function in k dimensions. I think that's quite all right. And what we can do is actually we can check the derivatives of this as well. Let's see. So I'm not going to calculate the derivative here, but we'll be doing that in the next lesson, probably when we look at logistic regression. Let's see. For now, let's take the partial derivative of the softmax of I with respect to its own score. So the derivative should be like this. So it should be like this. You can try to do it on your own if you're up for a challenge. Otherwise, just trust me on this one. So this goes like pi minus pi squared, which gives a very similar answer to what we got with the logistic function, is pi times 1 minus pi. So now we know that if this particular probability or this probability score, if this score was towards the higher end of the distribution, so this is closer to 1, then this part is closer to 0. That means the derivative is like nearly 0. So a small change towards the higher end of the spectrum does not result in a big derivative. And similarly, for the lower end of the spectrum, when this is 0, again the derivative is near 0. So for either end, for the top end or the bottom end of the spectrum, the derivative is really small because it doesn't matter much. And similarly, this is at its maximum value when both of these values are at 0.5. So we can see that this is again very suitable for our classification task. Here we can consider another derivative, which is how does the probability of I change when the score of a different class changes. So this is minus pi pj. Again, we can see what happens here. This derivative would be high only if both pi and pj are high values. If pi is a small value, doesn't do much. If pj is a small value, doesn't do much. But if they are both high values, then you can see that there's contention for like which category they should belong to. So there is a big change or considerable change in the derivative. So the logistic function and the softmax function, as we discussed, are really good tools for us to use for our classification tasks. Alright then, so I think this lecture is reaching a good time limit, so I will see you in the next lecture, and thank you for joining me.